Hello everyone. Hi, I'm Mary and here with Karim Azoum from the French Competence Center. We are part of the USCC project and with Pierre Aubert from Lab in Annecy. Together we organize the Grey Scott Thursdays and the Grey Scott School. So welcome to this new session of the Grey Scott Thursdays webinar series. As always, these weekly sessions explore key topics from the Grey Scott School curriculum and progressively prepare you for the summer school. A quick update before we begin. Registrations for the Grey Scott School are now open. Places in Annecy are filling up quickly, so we encourage you to register soon if you'd like to attend on site. We'll announce the list of satellite locations very soon, but you can already pre-book your spot. And of course, online participation remains available.
Could a simple chemical reaction teach you how to unlock peak performance on today's supercomputers? Welcome to the Grey Scott School 2026, a free advanced summer school on high-performance computing, designed for professionals from industry, public sector organizations, and academia. From June 22nd to July 3rd, 2026, join us in Annecy, France at LAP, at one of our satellite sites across Europe, or online via live streaming. All courses are taught in English. You can pick the courses most relevant to you or dive into the full 2-week program. You'll learn the practical behavior of modern hardware and how to write performance-optimized portable code. Week 1 focuses on CPUs, Week 2 on GPUs, covering architecture, bottlenecks, parallelism, memory, and performance analysis. All learning is built around a single challenge, simulating the Grey Scott reaction. Simple to start, yet complex enough to stress compilers and expose performance limits. You'll explore modern tools, languages, and libraries such as C++ 17 and 20, CUDA, Fortran, Python, OpenMP, TBB, Kakos, PyTorch, and more. The school provides ready-to-use container environments for smooth hands-on sessions. Expert instructors from CNRS and CEA guide you with live Q&A and community support on Discord. Satellite sites let you learn together locally without traveling. Want to host one? It's easy with our turnkey setup, sharing the school with your colleagues and ecosystem. You'll leave not only with hands-on HPC skills, but also an official certificate of participation. And you know what? You can start early with 18 Grey Scott Thursdays webinars, weekly from January 29th to June 11th, introducing summer school concepts and new topics. Whether you're an industry professional, engineer, researcher, or student, if you have programming experience and want to push your skills further, this program is for you. Register now at cc-fr.eu and start learning today. Grey Scott School 2026, Europe's leading HPC summer school.
So the school, as those webinars are free, fully online, and open to everyone. So please share the news around you. Put likes on LinkedIn or comments on the replays on YouTube. It really helps us, you can't imagine. So I'll put all the links in the chat very soon. And now today's webinar is a special one, as it is presented by Pierre Aubert himself, who will introduce GPU architecture, a key topic in modern high-performance computing. So Pierre, the floor is yours.
Thank you, Marie, for the nice presentation. So yeah, we will speak about GPU architecture for today. So for globally one hour, a bit more than 1 hour. So the idea of this webinar is to give you some order of magnitude of what we can compute with a GPU nowadays and how does it work. Not all the weird detail of the GPU, but most of them, in fact. So let's start. So first, GPU stands for Graphic Processing Unit. So it was invented back in the 80s. So the idea was to be sure that we will manage the drawing in the screen of pixels, of the stuff like, not pixel at this time because it was a cathodic screen, but you get the idea. And the point was to compute lots of simple computation at the same time. So it evolves around the time. And then at some point, people thought, yeah, it's nice for rendering, but I would like to compute with that because, in fact, we have a lot of computing power. And let's compute with that. And of course, vendors start to think about another way and say, oh, maybe we should make some graphics card, not for graphic rendering, but for computing. So GPU. And then comes some GPU that you already know. So K80, for example, Volta, so V100, A100, H100, Ada Lovelace, and Blackwell. So now we have Rubin. So Rubin, I will not present Rubin on this presentation. You know, it was a GTC last week. I will present that in June in the feedback of the GTC. So here we will focus on this architecture. So how does it work and what we can do with it. So in terms of architecture, we will start really simply with memory. So basically DRAM, so HBM3, HBM2, this kind of stuff. Then we have streaming processor, so SM in short. So here we will compute the kernel, in fact, what we want to express, to analyze or to simulate. And we have an L2 cache, so similar to the L3 cache of the CPU. So it's quite simple, in fact, roughly. We will get into the real details after that, but roughly it's quite simple. In a streaming processor, we have computing cores. Then we have all the stuff that we need to fetch and decode. As Adrien said in his CPU presentation, of course, you have to fetch instruction, decode the instruction, and execute the instruction on the cores. And generally, we have 2 lines of this in the streaming processor. And of course, since it's quite complex, we have everything to take care of the context of execution because we will have a lot of threads, as we'll see during this presentation. And also shared memory, so equivalent of L1 cache, not exactly because it's a bit more subtle, but globally it's the idea of another level of memory. So in terms of threads, it's a bit different. If I take a CPU, I have a CPU core here in green, and if I start a thread, the thread will use the full CPU core. If I use to vectorize, so I use specific instruction to vectorize and will use all the computing power of my CPU thread on my CPU core. So for example, I will vectorize in float 32, float 64, in integer, whatever, depending on the hardware. And if you are lucky, you can also vectorize some computing and some masking and some condition at the same time, but roughly you will lose a lot of instruction, one instruction and lots of computing at the same time. But of course, the problem is by default, there is no vectorization. So by default, you lose a huge part of the potential computing that you can have on your CPU core. And as I mentioned before in the C++ or for Vincent in the Fortran webinar, of course, you have to work a bit to tell the compiler everything is okay, please vectorize, my data are aligned, they are contiguous, everything is okay. So you have to work a bit to make sure that everything is working. On the GPU, it's not quite the same. So if I take a GPU core, is much smaller, in fact, here, and much simpler. And here we have a SM, so a streaming processor. And if I have a thread, the thread is running on a core directly. And the good point here is it's parallel by the hardware. So the hardware forces you to kind of vectorize. So it's not exactly a vectorization, but it's a kind of vectorization, in fact. We can call that a GPUification, but it's the same idea. And so you have a simple thread and you don't have to worry about what to do with it. Of course, it's a bit more complex than this, but we will come to that just after that. So in terms of hierarchy, on the bottom, we have thread. So they are linked to a GPU core, and we will execute the computing kernel on the thread. Then on top of that, we have a warp. A warp is linked to the hardware scheduler. So the scheduler will never treat a thread alone. It's always a warp. So you have generally 32 threads, depending on the GPU, but globally on all the NVIDIA GPU 32 threads, or the other vendor could change a bit, but you cannot change it. It's the hardware, and you have to deal with that. And all the threads in a warp are synchronous. So you have the guarantee that two threads on the same warp will execute exactly the same instruction. On top of that, we have block. So a block, roughly, it's linked to a streaming multiprocessor. So if you ask engineer from the vendors, they will tell you, okay, it's nice if you think about your block for a streaming multiprocessor, and everything will fit well, and you have to think about that. So it's not random. So it's 2 to 4 warp depending on the GPU, 64, 128 cores, depending on the GPU. We'll see that a bit later. And then we have asynchronous execution. So two threads of the same block will not be executed at the same time. If they belong to the same warp, yes, but if not, you don't have the guarantee. In fact, you have no guarantee at all. On top of that, we have clusters, so it's a bit recent. A few years ago, we get some clusters. So the idea is to manage block communication, because at some point, if we have so CUDA 12 with Aubert, to remind you a bit, we'll get into the detail after, but Aubert, it's 132 SMs and 108 SM for Ampere. And the problem is, once you want to do some communication between your block, even if on all the blocks you start on your GPU, you want to communicate with 10 blocks, stuff like this, you have to freeze everyone, do your communication, and resume your computing. It's quite annoying, so they add the concept of cluster to say, okay, I want to manage communication inside my cluster to simplify and to not block the full GPU just for few communication of few blocks. So that was a bit of a pity before, because of course you block your full computing power just for a few blocks, and unfortunately you did your job well, and you split all your job, but it's not taking account inside the GPU itself. And finally, we have the grid, and the grid is basically the full GPU. So we have 8,000 cores on Aubert, 7,000 cores on Ampere, and we can do a lot of computing with that. In terms of execution, of course, a thread makes no sense, as I said before, so we will see how it works with a warp. So we'll have instruction loaded 2 by 2 in the warp. So that's a classic way of doing things in the GPU. And once we have a condition, what happened is all the threads will execute the condition to see if it's false or true. Then we'll have the thread which have a true condition, we execute the then statement. Then all the other will wait politely, because the threads are really polite together. And then it's the invert, so they sleep and the other execute the else statement. So that's why generally once you write a kernel, everybody's telling you, please don't do some condition in it, because you will kill your performances, because you pay the 2 statement each time. Even if you have only one thread in the else statement for boundary cases, corner cases, you will pay the 2 statements. So it could be a bit annoying. So try to write less condition as possible. But of course, for boundaries or stuff like this, you need to have a bit of condition. So how do we map that? So we have a thread attached to a core, we have a block attached to a SM, and everything is in a grid. which is full GPU. We don't care about the cluster for now. Let's start simpler. So to get the thread, we have a thread ID, and to get the block, we have a block ID. To be a bit flexible in the ID, we have 3 dimensions, so X, Y, and Z. Of course, there are some limitation on the dimension depending on your GPU. You cannot put any value you can, but you can get your thread and say with your thread, okay, I belong to this block. I am this thread, so I have to compute this data in my table of data. So you have to do this kind of stuff to be sure that you get the proper value in your kernel. So the problem is, of course, once you start your kernel, which size? How do I decide the size of my block? So let's start with an Aubert project of 1000 elements, for example. First scenario, so I can say, okay, I will use 10 blocks of size 100. Why not? Let's start. Of course, the warp is 32 threads, and here I have 10 identical blocks with 3 warps fully filled with threads, and the last one, which is not really well used. Only 4 threads useful in the 32 threads. The problem with that is I will use only 78% of my GPU. So the occupancy, if you want, is only 78% here. So it's not really efficient. If we change our mind, we can say, okay, let's think a bit different and say, okay, I will use only 8 blocks of size 138. If I do that, I have 7 blocks of the same size but fully filled with threads, so with warp really used at their maximum potential. And the last one is a bit smaller because that's life. We don't have only power of 2 elements to treat, and then we have to finish here. But the good point is it's the case only for this block and not for the other. And so we get 98% of useful computing in the thread. So it's much better to use this kind of method. Of course, you have profilers to help you doing this kind of stuff. So in terms of read and write, one sector is 32 bytes in a GPU, and a cache line is 4 sectors, 128 bytes roughly. And if I want to access 4-byte elements or floats, for example, in my warp, I can get all my elements at the same time. It's quite efficient. I use only 4 sectors, which is really efficient. If I use 8-byte element for double, for example, I will use 8 sector. Everything is nice. And of course, this reminds you the CPU vectorization, that's the same idea. And the point is, of course, here once you define one thread in your kernel to say, okay, what will do my kernel, you have to think about the neighbor of your kernel. Of course, if you do nonsense and injunction table and stuff like this, will kill your performances, and we will see that here. About memory layout, let's pretend that we still have 32 bytes for one sector, and let's use this structure of coefficients, so 80 bytes with U, V, W, X, Y, and Z with tables also. If I map my structure on my memory, so we have the red block here, they are my structure, and if for some reason I want to read the value of U, for example, if in my coefficient, all the thread will jump in my memory, so it's not efficient at all. All thread will touch a different sector, and of course I will use only 4 bytes on the 32 I will read. So it's really not efficient. It's horrible, and you don't want to do that. Again, for a CPU also, you don't want to do that. So the point is, if you use a structure of array in the coefficient, so you have pointer here with the array that you want to use, you will have contiguous data, and then you can access U at the same efficiency that before, and then you use all the bytes you load are used. So always, it's always good to think about that. It's not magic. You will kill your performances always on GPU if you do not take account that. So let's talk about GPUs and order of magnitude now. So let's start with Ampere, so M100. So it's back to 2020. So I will present the SXM version. There is also PCI version, but we'll focus on SXM version. So 7 nanometer of wafer, compute is 8, 108 processor, as I said before, peak performance at 19.5 teraflops, so without tensor core. We'll see tensor core a bit later. 40, 80 gigabytes, depending on the version of the Ampere you want to have. 1.3 terabytes per second of bandwidth, so it's really, really fast. NVLink, 600 gigabytes per second of bandwidth. And the multiple instance GPU, so you can split the GPU in several pieces. So up to 7 in case of Ampere. So you can say, okay, I want 7 smaller GPU to use for my customer, for my colleague. You can use that. And we have really big bandwidth, so it's a bit too much for the PCI of this period. And we had a new hardware evolution related to that. Classically, once you want to read data from a disk to a GPU, you have to read data with the CPU and then put data from the CPU to the GPU. And it's really slow. And of course, the CPU can do much interesting stuff than just dealing with data of the GPU. So the idea was to say, okay, let's stop that and let's use GPU direct storage. So we will use directly the information, so the GPU can access directly the disk or the storage in general, and you can use directly that, and you can do interesting stuff with your CPU because CPU can also compute quite faster. So it's a pity not to use it. And you have the same idea now with the network. The GPU can access directly the network, and the GPU can communicate also with each other with the next version. So Hopper, typically. So Hopper, H100, so SXM5 and PCI. So 4 nanometer, the compute capability is 9, 132 SMs, as I said before, peak of 30 teraflop without tensor core, 80 gigabyte of memory, 3 terabyte per second on bandwidth, NVLink 900 gigabyte per second, MIG, second generation of MIG, so you can split Hopper in 8, but with confidential computing, so you cannot spy on an instance, you cannot spy the instance next to you. It was possible before. And once you split, you can always decode image and video. It was not possible before. If you split too much, up to 7, all the instances cannot perform that. So quite a fix. And we have a lot of computing precision. We'll see that a bit later also. In terms of thread acceleration, we have also some news with Hopper. So the TMA, tensor memory acceleration. So if I use a classic A100, so if a thread wants to access some data, the thread will read data from the global memory and put the data into the shared memory and then use them. The problem is, with this one, the thread will generate the addresses itself. The thread, of course, has other stuff to compute, and be bothered by computing address is not really funny, so not really efficient. So in H100, we have TMA, so tensor memory acceleration. So the thread will ask the TMA to get the data from the memory, and the TMA will perform the read and get the data into the shared memory. And during this time, the thread can perform other stuff. Quite also nice to save time. Then we have distributed shared memory. So in terms of block, once you want to share data, as I said, we have the concept of cluster. But before it, we were obliged to use the global memory, so to exchange data between blocks. And now with H100, we have a dedicated network to exchange data directly. So you can be more efficient if you want to exchange data on your simulation, for example. It's really, really efficient. The last point is about transaction barrier. So once you have a lot of threads performing some jobs, and then you want to stop everyone and synchronize everyone at a certain barrier. The first thread can perform other stuff, independent work to wait the other. But at some point, there is no more work to do, and they spin on each other until everyone is complete. Everyone has completed the job. So it's not really efficient. And on H100, we have the same ID, but with an increment count of the transaction. So we have an hardware counter on the transaction, and once the transactions are okay, everyone can start again. And the good point is, of course, if we have extra work to do, we can do extra work waiting for the other to complete. But once it's done, the thread will sleep until all the threads finish their transaction count. So it's much better. The thread will sleep and the other will be used more efficiently. So that's also a big improvement of this architecture. Not everything, of course, I don't have time to go into all the details, but you have also extra x86 function. If you have some question, I can go into this detail if you want. Then we have a Grace CPU, so we'll use also that. So 72 cores in ARM v9, so SVA2 with ARM v9. So 4 times 128 bytes. So once you vectorize in SVA2, it's a multiple of 128 bytes. So here it's 4. For Vera, it's 6, but we'll see that later. So 240 gigabytes of memory, 1.2 terabytes per second of bandwidth, bidirectional bandwidth. Some cache, so 64 kilobytes of cache, which is quite good, quite good, and L2 1 megabyte, L3 117 megabyte. And then we have local caching, so remote. So I will get into the detail here, of course. And then NVLink, so chip to chip, 900 gigabytes per second. Then we have Grace Hopper. We combine the two, and we get 40 gigabytes of bandwidth, 600 gigabytes of memory, the C2C 900 gigabytes per second as before, and a unified memory. So what's going on here? We have the Grace with its memory, with 500 gigabytes per second of bandwidth. We have the Hopper with this memory and 40 gigabytes per second on bandwidth. Then we have a chip-to-chip link here, 900 gigabytes per second. We have a dedicated network for the Grace with 512 gigabytes per second of bandwidth, and another dedicated network for the GPU. As I said, GPU can use in a network directly now with 900 gigabytes per second. And so with the memory management, before, so I will, with CUDA, classic CUDA, if I get some data on my CPU, I have to copy my data on my GPU with a CUDA memcopy, so host to device in that case. I copy my data on my GPU and then I can access my data. Everything is nice, no problem. Of course, it happened to everyone. At some point, you forget to copy your data and you have a big error. And CUDA is telling you, okay, I cannot access this data. There is a problem. Can arrive. Since 2020, late 2020, we have NVC++ and NV Fortran with some magic with the driver. So it's called unified memory. So you have your data on your RAM, and then the GPU wants to access the data. Of course, there is no data. So you have an error, and the error is caught by the driver, and the driver will perform the copy for you. And say, okay, no problem. You forget to do the copy, but I do the copy for you, and everything is fine. So it's not, it's a unified memory, but unified by the software, if you want. And then for Grasshopper, the CPU can have some memory, some data in the memory, and the GPU can access directly the data. And here it will say to me, yeah, but they are physically different hardware. So how it's possible? That's a good question. How it's possible? So if I get some data on my RAM for my Grace, Grace will ask the page system page table where this data is, and the system page table will say, okay, here. For Hopper, it's the same. We get some data in Hopper, ask the system page table, and then we get, okay, the data are here. Of course, with this design, if Hopper asks for this data, we get this data here. And we have an heuristic. If Hopper use a lot the data in the Grace side, the data will be transferred to the other part, to the GPU part. And for the same, Grace can access data in the GPU memory. And if Grace access a lot this data on the GPU memory, data will automatically be transferred to the Grace memory because Hopper use less this data compared to Grace. Another trick is inside the caches of Grace, Hopper can get some data in the L2 cache of Grace, which is quite magic, in fact. We get to have a lot of feedback about that. A lot of people running a big simulation or try to train some model, they use, in fact, this memory, the Grace memory, as a cache for Hopper. And then what you do is you have your data here. Hopper is using the data, so the data are moved automatically with the heuristic. And then once you use another data, the previous data are used, balanced in the CPU memory as a cache. And then you can extend the 80 GB of your Hopper with the memory of Grace, with a little price, of course, but quite interesting. If you don't want to read on the disk in time, because otherwise it will be really slow. Then 2024 we have Blackwell. So Blackwell B100. So Blackwell named after David Harold Blackwell. So it's a statistician and mathematician. So he did a lot of work in game theory, probability theory, information theory, and statistics. And so it's a 4 nanometer architecture. Compute capability is 10, 160 SMs. So 10,000 cores, 192 GB of memory. So a lot of memory. 8 terabytes per second of bandwidth. NVLink generation 5. So 576 GPUs. More computing precision, and then transformer engine V2, we will see that a bit later also, and decompression engine. Also, if you want to decompress really faster, you have an engine for that. CUDA if you want to encrypt your model, and the RAS engine. I have no time to talk about that, but there is a RAS engine also. So, in terms of precision, so Vincent also presented that in his precision webinar. So if you want more detail, I invite you to see the webinar of Vincent. But roughly, we have float 64, 32, TensorFloat 32, which are in fact float 19, but it's not sexy to say float 19. So TensorFloat, it's better. So it's a mix. You get the exponent of float 32 and the mantissa of float 16. Then brain float, and then the float 8. So a 5M2, a 4M3, it's in the title, so 5, 2, 4, and 3. Then we don't have infinite in a 4M and 3, but the other, it's okay. And then we have SP6, a 3M2, a 2M3, and a 2M1 for FP4. And they don't have none, not a number, as they don't have infinite also. And they are all managed by B100. So in terms of Blackwell superchip, we can have 1 Grace and 2 Blackwell. So we have a lot of number here, so I put them here if you want to have a look. I will not go into the detail, but the performance are ridiculous. And you get also nice performances. In fact, for Grace, 7 teraflop is quite nice for a CPU. So not so bad. So the Grace Blackwell superchip is a bit different. We start with a die. Then we have another die with a bandwidth of 10 terabytes per second between the two. And this is one Blackwell. Then we have memory of the Blackwell, 8 terabytes per second. Then we have two Blackwells. We have dedicated NVLink network for the Blackwell as before. Then we have a Grace with its memory, 512 gigabytes per second. The dedicated network for the Grace, 512 gigabytes per second also of bandwidth. And then we have NVLink for the two Blackwells. And the good news is, as for Hopper, the memory is coherent, so you have the same heuristic as before. So you can put your data on the CPU and then it will use on one GPU, from one GPU to another GPU, etc. You can do whatever you want. It's automatic. So it's really nice also to have this kind of stuff. So let's dive into the weird detail of a multi-stream multiprocessor for H100. So here you recognize it's not really a big mess. It's basically a copy paste of 4 parts. So you get L1 instruction cache, L1 data cache. Then we have the tensor memory accelerator. So for the tensor core, you have everything to load the texture. You have to load and store the data. You have the warp scheduler, as I said before, and the L0 instruction cache. And what we want to use generally is, for the classic computing, this kind of computing units for integer, for floating point 32 and floating point 64. So these are what we call the CUDA cores, in fact. And we have another stuff, which is the tensor cores, and we use tensor cores mainly for matrix multiplication, and they are really, really efficient. And we see that now. So basically a tensor core, the idea of a tensor core is to perform a matrix multiplication, a really simple matrix multiplication. And if I start from it and I bend a bit my matrices, I will get to this one. And the point is, to perform my matrix multiplication, first I do all the product at the same time, and then all the reduction at the same time. In 2 steps, I multiply my matrix. So it's really, really efficient. So in terms of size, of number of computing units, in fact, we have the V100 float 32, A100 float 16, A100 float 16, H100 float 16. So you increase and you increase more and more. And then the TensorFloat 32 for Ampere and Hopper. And here you get the full family from Turing to Hopper. So I don't have Blackwell because it doesn't fit in the slide. And the good news also is you can use them with Vulkan. So Vulkan expose cooperative vectors, so you can use directly the tensor core with cooperative vectors, so it's possible. You are not limited to only CUDA cores, so it's available since last year, a bit more, roughly. So you can use them now, no problem. So in terms of computing, why using tensor cores? Because CUDA cores, we have flexible computing. You can do whatever you want because it's you put in your kernel what you want to do and everything is okay. You have to take care about the data, about the read and write to be sure that you will have performances, but you can do pretty whatever you want. You still can optimize a lot of this computing. But of course, in terms of tensor core, as you see, it's not the same order of magnitude. So we have a faster computing for tensor cores. We have a larger choice of computing precision, and less power consumption also with this computing precision. And so here we basically have float 64, float 32 for CUDA cores, and float 64, TensorFloat 32, float 16, blade float 16, and float 8 for Hopper. And of course, you have to make sure that you have a matrix product at some point to compute, otherwise you will have a problem. But it's quite interesting also once you want to do some simulation or data analysis to say, okay, how can I make a matrix product from this computing? At some point, normally it's quite possible to do that. So you have to think and to search for that, but it's quite interesting to have in mind. And also it's much performance if you have some sparse matrices. So up to a speed up of 2 if you get some sparse matrices. So if you have zeros in your matrix, you can get extra performances. So if I add Blackwell in it, on the CUDA cores, we get CUDA cores here and Tensor Core here. So here we are above 1 petaflop for the computing performances. So TensorFlow 32, 1 petaflop, etc. for the other. Here it's 100 teraflops, so we have a difference between the two. And the point is, if here it's in logarithmic scale, if I put that in linear scale, we don't see Float64 anymore. And of course, people using Float64 are complaining because, yeah, it's slow and it's not really efficient. Okay, we have to deal with that. So what is possible? Because here it's an illustration of the size of the computing tensor core compared to their precision. So you can see, of course, Float64 takes a lot of space in the chip because the computing units are really big, and Float 8 or Float 16 or TensorFlow 32 are much smaller, so they can have more computing units because they are smaller in the chip. And of course, that's the answer why there is so little computing power in Float64, because it takes a lot of space, and also it consumes a lot in terms of electricity, because basically the power consumption is proportional to the square of the size of the mantissa. So of course, if you have a big mantissa, you consume much more than if you have a smaller mantissa. So that's also a big problem. So let's start with some precision of FP4, because of course, as I said before in the webinar of Vincent, FP4 is not what you expect. It's not FP4, in fact. So for Float 32, so I get 8 bytes of exponent, 33 bytes of mantissa. Float 16, 5 and 10, and etc., etc., etc. We'll not get into the detail, but the good point is the dynamic range in binades, so the equivalent of decades, but for binary number. So 277 for Float 32, 40 for Float 16, etc., etc., etc. So you get all the detail here. And in some research paper, you can get the information that we need between 10 and 20 binades to train some model. That's why they use this lower precision stuff. And here you will say to me, yeah, but Float 4, it's 3, so it's not 10. Float 6, it's 8, so it's not 10. And even, okay, Float 8, I can understand, 17, it's between 8 and 20, but what's the point to have this one? Because they are too small, in fact. Okay, so what's the point? And what is the trick under the hood? So it's a block format, in fact. So you get the metadata of your tensor, of your block, in fact. So in a Float 8, or maybe sometime a bit above, but classically Float 8, and then you have a block of the data value, so with the part in Float 4, typically. And then once you multiply two parts together, you get the real number you should compute here. So you have a scale factor, in fact, and you can do that for several, and it's okay. So if it's really expensive for the software to do this kind of computation, so the hardware does the computation for you, so you don't have to worry about that. It's automatic. And then if you want to do a dot product, for example, you have a scaling factor per tensor, and that's the classical way of doing things. And if you want to go in lower precision, you have one scaling factor per block. And typically, if you have FP16, you have one scaling factor per neural network. If you have FP8, you have one scaling factor per tensor. And if you use FP6 or FP4, you have one scaling factor per block. And that's the purpose of the second generation of transformer engine on the tensor core. So that's why you can do some magic, even with really low precision, because of course FP4 alone makes no sense. So you have to do some magic to make sure that everything is nice. So how does it work? So basically you have the value, the range of your tensor core the tensor you want to change, to modify in FP4. And what you want to do is to use the 4 and 3 representable range, for example, so the float 8, one of the float 8 representable range. And what you want to do is to put the same value, but a bit to the higher value here, to have a bit of margin here if you need to get extra precision, as Vincent presented. Of course, once you do some computing, you may need some precision here, so you force a bit this distribution to be on the right, a bit more on the right. And then what you are doing is I use a shift to change the range, to make sure that it fits in my representable range, and to make sure that I still have a bit of margin. And then I round to the 4 and 3 range once I do the computation. And to get back my result, I round to the tensor range in the opposite way. So it's a kind of intermediate trick, as Vincent presented. We have the bunker rounding, so once for you, once for me, thing like that. You have rounding to infinite, rounding to 0, and then this one is you have rounding to one range and rounding to another, to be sure that you lost as little as possible precision. So that's the trick under the hood. So in terms of performances, we get FP4, so 1.8x on inference compared to FP8. So even if some FP8 involved in it under the hood, of course. So FP4 with PTQ, with Quat, with all the weird stuff of the people who want to train model and stuff like this. So that's quite not really my point. So we will have, but if you want to get the information, you get the information here. So they train on DeepSeek, on Llama, on Nemotron, to make sure that everything is okay, with SVD quantization also and they get equivalent performance compared to BrainFloat 16, which is quite nice. And there is a CUDA support since CUDA 12.8. So if you want to play with that, it's possible also, just to see if it fits your needs. And in terms of computing, let's have a look also in terms of float computing. So in float 32, as Vincent mentioned, we have a sign, mantissa, and an exponent. And if I do the example with a float 12, because it doesn't fit in my slide to have float 32, I have exponent and mantissa. And if I want to perform an addition, for example, on the two A and B, I want to be sure that B will have the same exponent as A, so I can compare them, I can do the computing with them. So I have to change the exponent of B, and then I get the exponent of A, and sometimes you can lose some precision because I cannot fit the value I have in my mantissa, and then I can compute the operation, but of course I might lose some precision for this example. So that's why sometimes you lose some precision. It can happen. That's why also I insist on that. I re-insist on that. You have to make sure that your data are well conditioned. Otherwise, you will have a lot of precision problem, and it's not really nice. So let's try to emulate float 32 computation with BrainFloat 16 to see if we can have a speed up. So let's start with multiplying polynomials. So we have polynomial A and B. So with coefficient K0 up to K2 and A1, A0, A1, and 2. Same for B. If we multiply A and B, we'll get this horrible formula. And if I rewrite this formula as a product, if I multiply A and B, in fact, I have a tensor product. And if I do the same with K, I have another tensor product. And then I can do a dot product to get my result. Okay. If I do the same for BrainFloat 16, so I have float 32, I pretend that we can express float 32 by a polynomial with BrainFloat 16 and 3 Brainfloat 16, and we do the same. So we have known coefficient here, so 2 power of 0, 2 power of -8, and -16, so to make sure that everything is working. If I multiply A and B, I will have my tensor product for A and B, and the same for K, but we already know K because we know the coefficient, so we can compute all the coefficient before. And then we do a dot product, and once we reduce, we will reduce with an ascending sum. Again, think about Vincent. If you sort your data and you do an ascending sum, you will keep more precision than if you have random values. So it's much better to do that as it's done like this in this emulation. So in terms of emulation, if I want to compute some matrix product, I get my A and B in float 32. I get my matrix K with my coefficient. I slice my values into Brainfloat 16 with CUDA cores. I do the same for B. Then I perform my matrix product with tensor core. As you saw before, we get much more computation power with tensor core, so we use them like this. And then finally, with this tensor core, we use the unslicing method with CUDA cores again, and we get the result with float 32. The good point is, once you want to multiply matrices, you want to have big matrices, because otherwise you will not fit well the tensor core. Here, with this method, with this trick, even if you don't have so much value, you will increase the number of value by the slicing, so you have a better fit in the tensor core. So it's a nice trick also for this kind of stuff. So in terms of performances, you have on this weather simulation, they get some 2.4 speed up for the matrix multiplication, which is quite nice, in fact. And here the point is with the QBLAS with Brainfloat 16, you can get in some cases more precise results. So here, the more it's picked, the more it's precise. And here you see in the QBLAS FP16, you have a much precise result, so more picked distribution than the classical computing, because of course it's not exactly you cannot get exactly the same multi-set, a bit more. So you can, in some cases, have better precision. So it's nice also to have. So you have a speed up, and on top of that, you have a better precision. So it's nice to check. And people for the weather forecasting are really demanding on this, because they use a lot of higher precision computing, and they check this one also. And they're really glad of that. But we can do more, in fact, because people are also complaining, because FP64, there are less FP64, so we have to deal with that. Okay, so float 64, it's 52-bit of Mantissa. So we can do a linear combination of 5 to 9 int 8 and see what's going on. So we have float 64 A and B. We have, let's pretend 56-bit of Mantissa, so S equals 7. Of course, 52 is not possible because it's not a multiple of 8. So we have to choose between 48 or 56, and then you take the better that you want, or even less if you can. Then we do the slicing for A and the slicing for B on the CUDA cores as before. Then we perform the matrix computing on the tensor core, and we unslice with a big tensor core here, and we unslice with the CUDA cores here with K, so with an ascending sum as before, and we get the result back for the matrix computing. Nice. And they did the test with some material science here, so they get a speed up of 2.1 here in this particular simulation, and they did a full study on that. So with different precision, because here you can emulate, so you can use the precision you want. You are not stuck with 32 or 64 or whatever you want. You can do you can do 72, 64. You can do 56, 48, or 40, and float 64 it's 52, so it's in the middle here. And of course, in terms of performance, if you have small matrices, we'll have a big problem, because it takes time to slice the matrices. No, of course, you need to have a big matrix, but here, if you have a big matrix, you always have a little speed up, depending on the precision. And on really big matrix, if you have a lot of node here, a lot of cells, you can have up to practically more than a speed up of 4 here in term of speed up. So it's quite interesting, in fact, even if you are not if you want to use Float64, you can use a different precision if you want. So here's another example with QR factorization. So the idea is to compare the classic Float64 here in black dot here with 48 bits here in orange square, or in diamond here 56 bit, or in 64 bit with 8 for the triangle, the green triangle. And since it's not the end yet, you have also an automatic way to do the computing. So you tell the QBLAS, you tell the precision you want, and the precision is chosen automatically. And there is a margin, of course, compared to the precision you want, but it's quite nice also to have this kind of stuff. So it was tested on 500 matrices, so normally it's quite nice. So if you want to have a look, it's okay. So in terms of emulation, the current algorithm will fall back every time on Float64. It is not possible to emulate. Sometimes you cannot slice because of the difference between the bigger value and the smaller value can happen. And again, think about Vincent. If you have a really badly conditioned matrix, you will have wrong result even in Float64. So maybe it's better also to precondition it, and then you can use emulation. In CUDA, so it's a little spoil of what I will explain in June, but in CUDA, QBLAS, you can use the emulation right now if you get the last one. So with QBLAS emulate double precision, you put that to 1, and then it will emulate double precision for you. So you don't have to change your code, just it's an ugly environment variable, but that's life. And then you can send the strategy also, so performant if you want to have an automatic way to determine which method to use. And you can also use eager to say, okay, I want to simulate just to see if it's possible. Maybe you will see also some problem in precision if you do that, but maybe it can help you also to fix it later. And you have the QBLAS set fixed point enumeration max mantissa bit count function, which is really way too long to set the precision in bits that you want for your computing. Then it will spread into other libraries, so for QSolver and QTensor also. And there is now some tools for to evaluate the precision on the GPU. So it's a kind of cadenas or of Verrou, if you want, for GPU. So I will talk about that in June. I don't have time here, but you have some tools available right now if you want to do some magic with this emulation. So to summarize, before people were complaining about tensor cores because if there is no emulation, you get the raw hardware, in fact, and they complain because there is a drop of Float64 computing power between Hopper and Blackwell, and also less with Rubin. But with emulation, normally, people are really nice. So it's a Ozaki 1 simulation if you want to get the algorithm and the paper of the algorithm. And here they are happy because there is an increase of the performance. So normally it's okay. But you have to take account that, again, it's consume a lot, and classic Float64 consume a lot, and you use a really small part of your GPU if you do that. And if you emulate, you can use much more part, and you have extra algorithm also to use intermediate precision, so you can switch to BrainFloat, to integer, to a lot of stuff to increase your computing power. So you use the GPU at its full potential mainly. So it's quite nice. So last question of the day. How many threads do I want to start on my GPU? If I create my thread on my kernel by hand, how do I know how many threads I want to start? Okay, let's try to answer this question. So I did the test with a Gray-Scott reaction on some GPUs, so GPU of MUST, the computing center of the lab, from K80 to M100, and we get this kind of performance. So with the number of threads I started on my GPU and the elapsed time, the full elapsed time of the computing in seconds. So basically, if I try to think as a CPU and say, okay, if I want to vectorize, I want to start roughly the same number of threads, the number of cores of my CPU, and maybe one more for the I/O, but not too much. Here, if I take A100, for example, I have 7,000 cores. So I cannot fit 7,000 core in my computing, but I use it with 12,000 here. I get really bad performances. So I do not have enough thread. Of course, I want to be here. And here is 700,000 threads. And between the two, I get a speed up of 41. So if you don't start enough threads on your GPU, you will kill your performances. Even if the GPU will say, okay, it's nice, but no, the GPU will say it's nice, the profiler will say it's not really good, but not catastrophic, and if you use your system monitor or your Insight monitor, the NVIDIA server settings monitor, will say to you, okay, it's not really good, but it's not catastrophic. But in fact, it's catastrophic. So you have to be sure that you start enough threads on your GPU, because you use some they call that waves. You start a lot of threads to be sure that everything is faster. I don't have time here to explain that in detail, but we'll see that in the school. So to have enough threads, you need to express parallelism also again. So if I have an element and I have a lot of independent elements, I can compute with a lot of parallelism. So if I take the example of a particle, I have a position x, y, and z, for example. And as I explained before, I want to make sure that I separate my different components, even if they have the same type, because at some point, maybe I will need to do some dot product or cross product of the components. So I don't want them to be adjacent in memory. So I want to split the storage to have a nice computing. And then I can have a vector, a lot of tensor of that to be sure that it's efficient. I can do the same for the velocity. I can do the same for acceleration, for example. And then once you have that, you can ask yourself, okay, if I compute the first particle and then I compute the 19th particle just after that, is it a problem? Do I need an ordering? If the answer is not, maybe you can say, okay, I can vectorize. I can treat 8 particles at a time or 16 particles at a time. And if you use your GPU, you can say, okay, I want to pass through everyone at the same time with my GPU. It's okay. And at the end of my computing, everyone will be okay. I don't care of the ordering. There is no problem of back dependency, so it's nice. So if I do the same with events, could be a bit more tricky. If I have independent events, so independent computing, because I have stochastic events, for example, I have a lot of parallelism. But maybe it's not enough. Maybe if I put my event here on my GPU, for example, on my laptop, I can put maybe 6,000 events of my experiment to do the analysis. 6,000 is not enough. If I launch 6,000 threads, it's way too little on my GPU. So I want to increase the number of threads. So I want to increase the number of parallelism. So I want to break down my event and say, okay, maybe I have some captors in my event. So maybe I have some pixels or some calorimeter and some line in the calorimeter, stuff like this. And maybe it's still not enough, because I will have more value to treat, so more threads, but maybe it's still not enough. So I can break down my pixel if they have a time response, for example, pulses, waveforms, slices, can also increase the number of computing I can do at the same time in parallel. So here I have a big tensor, and I have to ask myself, okay, what is the ordering of the data in my tensor? So what is the contiguous axis? What are the other axes? And to answer this question, we have to ask ourselves, okay, what do we want to do with this tensor? What is the computation? What we want to do? And then if it's data analysis, maybe the first step will be to calibrate. So to take voltages and to convert them into number of photons or to energy in a calorimeter, stuff like this. And let's pretend for this slide that the calibration is independent of the storage. So we get the best performances even if we change the ordering of the tensor. So tensor does not affect the performances. Of course, if you change the tensor and you get bad performances all the time, it's not a good point. You want to have the best performances at the beginning. Let's pretend it's the case. Okay, so let's check the second step of the analysis. It will be maybe an integration. So I want to sum my slices to increase signal over noise ratio with weighting, for example. So here I said integration, so I have to ask, okay, integration means reduction. Reduction means back dependency, and back dependency means I don't want to have this data and this data contiguous in memory. So all these data, I don't want them contiguous in memory, otherwise I will kill my performances. So logically, I want to have this axis as contiguous data. So the last axis in C or C++ and the first axis in Fortran, because it's not the same convention. So here I get the full slice, one slice of all the pixels. I can sum this slice to another slice with all the pixels, and it's okay. No problem, no back dependencies, everything is nice. So I can vectorize, so it's okay also for CPU. Your CPU will be happy if you do this kind of stuff too. It's okay for the GPU, of course, but it's okay at a much larger scale, in fact. And you can vectorize the integration, well, because the integration does care about the ordering. And you can also vectorize the calibration, because the calibration does not care in that example. Then the second axis will be this one, to be sure that I have my first slice of everyone, but the second slice is not too far in memory. So to be sure that the fetch will be quite efficient. And then, of course, the first axis will be this one on the event, and then, or the really non-contiguous axis, depending if you are in Fortran or in C++. So the non-contiguous axis will be this one, and you can parallelize on core, on nodes, on cluster, on GPUs, in fact, if you want. No problem. There is no problem because all the events are independent, so you can split that as you want. No problem. This is a reminder also, this is really important. Computing drives data storage. You cannot store your data randomly and hope for the best. It's not possible. You have to ask yourself, okay, what I want to do with my data, what I want to compute, what is the ordering or what the order of the step, what are the needs of the step to be sure that everything is passed. And then you can have a nice data format. So in terms of computing, we always have to think about backend also to be flexible. So for example, here we talk a lot about tensor. So use a lot of tensor to do some computing. And then you have a linear algebra backend to say, okay, I abstract myself of the linear algebra backend I want to use. And then I use, for example, CPU backend, so MKL, Armadillo, LAPACK, Eigen, stuff like this. Or maybe for NumAnode also, to deal with NumAnode, because as Sebastian mentioned in his presentation of on the memory, it's really difficult to manage that well. So if people are dealing with that for you, it's nice. And for the GPU part, you can also say, okay, let's try CUDA, let's try cuBLAS, let's try Cocos or Sycl or Vulkan or whatever backend you want to use, or compute with a K if you want also. So you have some flexibility and you are not stuck with lots of calls in your code, and you don't have flexibility to change if you want to search and check something. So it's nice also to have this in mind. And then you can use multiple GPU, of course, with that. And it's a standard interface. So it's nice also to have a standard interface. So you have to do that yourself for now. There is no standard interface right now. And in conclusion, so express as much parallelism as possible before trying to do some GPU stuff. Otherwise, you will have a problem. So 700,000 threads for an A100 on the Grayscott. So it's really a huge amount of threads. So if you don't have good performances, try to increase the number of threads just to see what's going on. Of course, you cannot normally have more than several million threads, because at some point you will have a problem with the scheduler. But try to start as much as possible threads to increase your performances. Use simple types of vector, matrix, tensor, of primitive types to be sure that everything is efficient, and to use CUDA cores and tensor core efficiently, not weird class and class and class in a table of vector or stuff like this. Nice data format. And then you can use linear algebra with that, with dot product, matrix multiplication, Saxby or Adama product. And this is a standard interface, so you can use all the CPU library for that, or the GPU library for that, and other library. If you want to create your own library, you can have a nice interface to check and to be flexible. And thank you for your attention, and hope it was interesting for you. I will take some question in the chat if you have some question. Yeah, SM is streaming multiprocessor. Yeah, good point. Yeah, I said that at the beginning. A question from Adrian. What are some high-level difference of the AMD architecture? I'm not really familiar with AMD. You have to ask the question to Adrien. But in terms of high level, not sure there is some difference. You have memories, you have equivalent of tensor core, you have equivalent of CUDA core. It's not the naming convention is not the same, but you get roughly the same stuff. Question from Claude. What is a good data set preparation when you talked about precision? Yeah, so it's more a question for Vincent, but I will try to answer that also. Depend if you talk about data set about training, or if you talk about data set about computing in general. Generally, you want to have good condition data. So you want to be sure that between the higher value and the lower value you have in your tensor, you don't have too much decades or too much binades in this case. Otherwise, you will have a precision problem. So that's why typically once you want to compute, as Vincent mentioned, once you do some simulation or data analysis, you never use the unit as an input. You scale everyone. If you want to do some computing, for example, in the galaxy, in the universe, you don't use centimeter, you use parsec, or you use other scaling. If you are really small, you do a really small simulation, you don't use meter, you use maybe a nanometer or femtometer or stuff like this, or you use reduced unit, or even unit which are not used in the real world, but just to make sure that you have values, the best precision. Normally you get, if you get the value you use around 1, you get the best precision here in with IEEE 754. You get the best precision here. So you want to know your data and to be sure that you can do that. You can mitigate the problem. Okay, little spoil for June. You can mitigate the problem if you do some blocking in your matrices. So if you have a badly conditioned matrix, but you treat it by block and all the blocks are well conditioned, it's okay. You will have good performances and you can emulate and you can have good speed up. So that's a part of the news for June, but I can speak a bit about that here. So yeah, it's important. You have to know your data well. So now we have tools to check that. So there is, as I mentioned, there is CUDA, there is Veru, there is Verificarlo, and we have tools coming also for GPU. So you can you will be able to do that here. So question from Luca. In terms of GPU architecture, I heard that memory location can do a huge difference to, I show that, I think it was last year. You can have more than a speed up of 2 if you break your locality and then you have the location. Yeah, so yeah, it's important. Do you have any insight about shared constant global memory texture? Okay, so one point about texture, I can start with this one. So the texture memory is not really fast. So Adrien learned this lesson last year. So unfortunately, texture memory is not that fast compared to the compute memory. So don't use the texture memory to compute. It will slow down your computing. And then you have a hierarchy. So there is really interesting presentation on the GTC about this kind of optimization. You have basically you have four kind of memory. You have the global memory, you have the shared memory, you have the tensor memory, and you have the, I don't remember the name. What you can do is to prefetch your computing if you really want to have the best performance possible. You can, once you do a computing, you can interleave the computing and the prefetch of your data. So you compute your data, you do the prefetch of the next step during the computing, and then for the next computing, it's already in the right place. So it's really difficult to do that, but you can do that if you really want to have the best performances. But global memory, it's the equivalent of the RAM, so it's slow, but you have a lot of space. Shared memory, it's really fast, but you have not so much space. And then you can have tensor memory, which is really fast for tensor computation, and you can use all the memory at the same time also. So yeah, you have to jungle with everything to be sure that it's fast. Also, will you cover tiling in June? Yes, I will. I don't have time for this, but yeah, we will cover tiling in June a lot. For the multiple GPU parts, here I don't have much time to. I removed a lot of slides to be sure that I will not have a 2-hour presentation. So yeah, I don't have time to talk about tiling today, but we will talk about tiling during the feedback of the GTC and during the school also, because it's the purpose of the school. It's to have multiple GPU simulation with the pyramid algorithm, with all the stuff that we did last year, but at much higher scale. So yes. Question from Eduardo. If I understand well, does moving an object-oriented code to a GPU-oriented strategy usually require migrating to SOA data layout? Yes, that's a really important point. And all the people dealing with GPU computing pass through this path. So you start from knowable data format with a classes and classes and classes and classes because someone told you that it's nice to do that. It's not. And then you want to feed that in a GPU, and the GPU cannot do that because that's life. So you have to rethink your architecture with GPU proof architecture. So GPU proof data with a big tensor. Even if you want to slice the tensor to have parallelism, it's okay, but you have to have a tensor with simple types. If you do that, you will still have a speed up on a CPU before you pass on the GPU. So it's really important to do that. So yeah, it's not easy because it's not a nice path because everyone told you that it's okay, and in fact it's not. So you have to change. But if you do that, you will have much better performances also on CPU. So it's that's in fact a nice point. If you want to pass through a GPU, you improve your code and you get better performances even on CPU. So you are happy, even if the performance of GPU are not as good as you expect, you have better performances on CPU. So you're happy too. So it's you have to get this one. And again, now compiler are a bit smarter, so you can do with stuff on a GPU, but you will kill your performances. So it's better to have a nice nice data format. Data format is the foundation of your performance. If you don't have a good data format, it's not possible. So question for Maxime. First of all, thank you for the nice presentation. Thank you, Maxime. Do you think software should optimize their CUDA kernel more generally code, given a CUDA version on CPU card instead of code working with most version of GPU card? I didn't have this problem. For now, I use normally globally optimized kernel, but I compile generally for the GPU I want. So I write generic kernel, but I compile the kernel for the GPU I want. If you want to do really specific optimization, you can use PTX. So you access to the intrinsics of the GPU, but it's not portable anymore. But yeah, normally the compiler is really nice. So you can express your kernel in an efficient way first. So you don't want to do some injection table. You don't want to have bad data format, stuff like this. But if you do that, normally the compiler does all the magic for you. So you don't have to worry about that. If you really have some problem of data management, for example, here you have to give some hint to the compiler or to say, okay, I want to use this memory or this memory explicitly. But you will have in all GPU, you will have a shared memory, so you can use that really well. So yeah, normally it's not. In fact, it's useful. In fact, there was a really nice presentation last week for someone who do some attention layer optimization with all the memory at the same time to compress all the computation and do some prefetching and stuff like this. But it's really for a particular point. First, try to have best performances with genericity, and then if really you want to be in production with this particular GPU and you struggle to get the performances you want, yes, but not before. So question from Frederick. In a SM, FP64, FP62 into 8 core, physically separated processing units. Yes, that's why it takes a lot of space. So maybe there is some trick between float 6, float 4. Maybe there is a mix or something. But for the classical computing unit, yes, FP64 is not the same as FP32. In fact, it's not FP42 for Tensor Core. It's TensorFloat 32. You don't have Float 32 on Tensor Core. Maybe on AMD, but not on NVIDIA. So yeah, they are separated processing unit. How should we understand as bit processing? No, it's not bit processing. It's not grouped. Maybe for the integer, maybe there is some trick, but for float 32, float 64, float 16, or brain float, they are. In fact, maybe brain float and float 16, maybe there is a small mix, but for the other, there is no mix. So yeah, could be nice, but maybe it's quite difficult to do that. So they copy paste the different stuff. But yeah, for now it's different. So thanks from Luca. Okay. So question from David. Thank you for this nice presentation. Do you have a recommendation for a course document book about C++ data-oriented programming in the context of scientific computing? I have my lecture if you want. If you want really good lecture about that, in fact, what we do in the school is quite okay normally for you, depending of your level, in fact, and how to organize your data efficiency. Yeah, how organize your data efficiency? It's up to you to answer this question. The question is, what do you want to do with your data? So if you want, as I mentioned before, if you want to read, you have a complex data structure and you want to read only this and this value, maybe you want to extract this value into tables to say, okay, I want to compute this once and then maybe the other afterward. So you want to have simple layers of data. Even for the CPU, it's the same. For the CPU, you want long, simple data, so you have a prefetch, and the CPU will help you. The GPU also has a prefetch, so you can do that. You can do that well. But yeah, for C++ lecture, You have the Idris lecture, the lecture at Idris, which are really complete for that. Some other computing center may have their own lecture. You have a lecture from Arnaud in Maisonette. Normally, you have some lecture, mainly more in the ISR part, but you can have also some developer lecture on that. I know that Pascal from Maison de la Simulation, the director of the Maison de la Simulation, they are trying to revamp all their lectures. So normally you will have a new lecture also for that. And also you have the lecture from the school if you want to have that. But yeah, you have to practice. But basically, even if you want to treat Shadok, for example, with a name, with a value, with whatever you want to split that into a structure of tables or structure of tensor to be sure that it will be efficient on your GPU. And then you have flexibility. You can load certain data, not all the data, or some debug stuff, not debug stuff. So yeah, you have to worry about what to do with your data. It's important. And normally, for now, I didn't had some problem once one algorithm wants data in this ordering and another algorithm wants data in another ordering, and then you have to do some conversion between the two. But it's better to do a conversion rather than to have a slow part and another slow part. You have a fast one and then you convert and you have another fast one. Or maybe you can have something on top to say, okay, maybe we can make sure that everyone is okay and have an extra data format. But you have to play with that on a blackboard, on a whiteboard to be sure that everything is nice. In fact, yeah, you maybe you don't want to forget that the design is really important. So spend time on your design, spend time with your colleague on a whiteboard, on a blackboard to check everything, to be sure that everything is nice, to be sure that all the scenarios that we want to have are okay. So you will have best performances with that, rather than that to dive into the development without caring about that. If it's really long, it's better. You can have months of design and then a few days of implementation. It's way better to do that. So spend time and check with a small problem to be sure that you have the right data organization. François, a question from François about masking question. You could talk a QDSL. Yeah, you can use a DSL if you want. Yeah, I didn't talk about that because it's more about hardware today. But yeah, you have kernel tuner, which is I think it's written in Python, but we don't care, just to generate some kernel. So you have kernel tuner, which was developed by the guy who developed CUDA, if I remember well. And the point is, once you start your kernel, you don't know what is the size of the grid of the block, and you want to explore a bit the size of this part. And kernel tuner is meant for that. So it will start a lot of kernel, lot of tests with different grid size and block size to figure out what is the optimum of your computing, so you can then get this back for the production. So it forces you to do some performance tests or unit tests to be sure that the results are okay. But you can use this kind of so it's not really a DSL, but kind of, you have little configuration to say, okay, I want to explore this and this and this and size of block and size of grid, and it will do all the matrix for you and explore and get the best one. So you can have this kind of trick if you want to optimize your kernel. It will be more for the next part, when we will explore Fortran on GPU and C++ on GPU and Cocos and stuff like this, for more the implementation part. Here it's more the hardware, but yeah, you get the idea. Yeah, you can have maybe Python DSL. Yeah, mainly, yeah, François, yeah, it's gem focused. Basically, if you want to have performance on a GPU, try to do a gem. So general matrix multiply. or a diagonal matrix multiply or whatever, but having a matrix multiplication at some point, then you will have the best performances. And another point maybe also is maybe do not force you to think about one element to compute or one event or one part of the simulation to compute at a time. Try to figure out on your blackboard or on your whiteboard, okay, if I have a matrix of events to treat, what are the implications in terms of memory, in terms of kernel? Maybe I don't want to write my kernel to treat one event and call the kernel 1,000 times on my GPU. Maybe I want to write my kernel to compute 1,000 events at the same time. It will be more efficient. And for the CPU, depending on the cache, it could be the same OC, not with the same value, of course, because the caches are not the same size, mapping is not the same one. But yeah, you have to also think about that, because if you say, for example, I have one event, I want to sum all the pixel of my event because I want to get a charge of my event to see if I want to continue the analysis or not. You can say, okay, I have a sum to perform. So it's annoying to do that in a kernel. But maybe you will realize that, yeah, but if I have 1,000 events to treat, it's no more a sum. It's a matrix product. It's a matrix vector product. And I have my vector. I have my a vector of 1 here. I have my matrix here. I do my matrix vector product with 1, and I get all my results at the same time. And you get more parallel computing also, because you don't care. You don't have to worry about, okay, I want to have a number of events which is a multiple of the number of threads that I want to put on my GPU, but it's quite annoying and I will have the block. And no, you multiply your matrix and everything will do the magic for you, and you don't have to be bothered with that. So by having a step back and say, okay, maybe I want to compute several elements at the same time, or several events, or several cells, or whatever at the same time, or several grids at the same time, maybe you will make sure that, okay, maybe there is a matrix product hidden in that. So I don't have to write my kernel anymore. I just want to perform matrix product. And then you are forced to use tensor data to be sure that your matrix product will be efficient, even if you have sparse matrix or stuff like this. So yeah, it's important always to think about matrix product. Even if you want to use, yeah, maybe I didn't mention that also, but if you want to use directly tensor cores, you can use them by hand if you use PTX or stuff like this, but it's quite annoying. Personally, I prefer to use QBLAS or QFFT or this kind of library to target the tensor core for me, because I don't want to do some reduction on my kernel. I don't want to be bothered with this kind of reduce in logarithm, because all the implementation is done for me, and I don't want to be bothered for the FFT to do the same kind of stuff. Everything is done for me. So if you step back, maybe you will see that the optimization is quite nice also to have this reflex. Question from Frederick. Thanks for the answer. I don't remember the question, but okay. So there is a risk that Float64 core disappear from GPUs in the future. I'm not sure that they will completely disappear, because at some point, again, if the slicing algorithm does not work because you don't have a good slicing, you cannot perform the slicing, so you cannot use different precision unit. But maybe they will also decrease a bit, because you have, as I mentioned, it takes a really big part in the chip. And if you emulate them, you can use all the other parts to do the same computing. And for one Float64 computing, you can have 8 Float8 computing or stuff like this. Not exactly, because you have some subtleties, but roughly it's the same, the order of magnitude. So if I have more Float8 or more int8 computing unit, I can emulate more Float64 and more Float32 also, even if there is no Float32 in tensor core, because it's tensor float, so it's float 19 and not float 32 exactly. So you can have extra precision. And again, Okay, I want to use float 64, but maybe 48 it's okay. Or float 40 it's okay. So you have also more way to play with the precision. Maybe at some point, what I dream about now, it's to make sure that the hardware does the slicing for you. As for the float 4, you have your float 8, you split your float 8 into one float 8 and several float 4, and then you do the computing. Maybe it will be possible at some point that the hardware, you get your tensor in float 64, for example, and the hardware does the slicing for you in the precision, automatic precision that you want, and then you do the computing, and you get back your float 64 result at the end. If there is some magic like this, it's okay, no problem. I have float. I want to simulate weather forecasting simulation, stuff like this. I want to have float 64 because I know my problem. Okay, why not? I have float 64. I do the computing. I get back my float 64. If there is some magic happening in between the two, but I get the right result, it's okay. So why not? Maybe not disappearing. Yeah, in short answer. But less. Why not for the corner cases? And again, it forces you to think about your precision and to think about, okay, I don't want to use float 64 because I don't want to worry about. I want to worry about. I want to check which precision I want to use, and I know the precision I want to use, and I condition well my matrix so everything is okay. And if everything is okay, normally you can emulate, so you will be happy normally. Question from David. Yes, do you have the link of your lecture? Yes, but I don't want to spoil you. So you don't get the link of my lecture before the school, but you get the link of the previous lecture if you want. Of course, we will go in more details in this lecture compared to last year. But if you want to play a bit to see what was the starting point last year, you will have some stuff. So we manage basically one GPU. So the idea is to manage GPU as much as possible, and with the data ordering, with kernel optimization, with the slicing, with Insight, with the profiling, with everything for C++, for Fortran, for Rust, for Vulkan, for Sycl, for NVC++, for NV Fortran, for everyone. So yes. So yeah, you can also have a look to the NVIDIA lecture. So it's quite complete. In fact, you have a really nice lecture of Athena, also Athena Elafru from last year, to explain to you how to optimize well all the data scheduling and all the scheduling. So it's really complete. So it's really high level. So you have to fasten your seatbelt to be sure that you can follow. But yeah, it's really interesting also to have this kind of lecture. A question from Maxime: which is the best Ozaki scheme? So the one I presented to you is the scheme 1. So Ozaki scheme 1. The second one, I'm not really familiar with it. I checked the presentation yesterday from Ozaki himself. But yeah, this story about moduli and not masking, and you have twice the performances of the first one, but you don't have the flexibility of the first one if you need to change the computing on the fly. For example, you say, okay, I want to emulate my floating point computation with, I don't know, 5 integer, 5 floats or whatever, and you do your matrix and it's not enough. You can have a 6th one and without recomputing the previous one and adapt your computing on the fly. It's not possible with Ozaki 2. So maybe for flexibility, Ozaki 1 is better, even if Ozaki 2 is faster in terms of computing, particularly a speed up of 2 in some cases. So it's quite interesting. But yeah, I think it depends. Yeah, it should depend on the number of splits. Yeah, and the type of representation you want. Yeah, but basically, if you don't really know and you want to have some flexibility, Ozaki 1 is better because you can add more slice in your computing on the fly, and you cannot with Ozaki 2. You have to drop everything and to restart with a higher number of moduli. So yeah, it's So for now, I think it's mainly Ozaki 1 implemented in Kublas. Ozaki 2 will come at some point, but for now it's mainly Ozaki 1 with some tricks. So it's not exactly the Ozaki 1 of the paper because engineer from NVIDIA changed some stuff to improve it a bit in the implementation. So it's not exactly the same. You have another paper for the implementation on Kublas. So if you want to have a look, but yeah. So François said the Tensor Core FP64 can disappear. Yeah, there is a drop of performances for FP64 for CUDA core and for Tensor Core, but again, you can emulate the Tensor Core, the match product with the Ozaki scheme, in fact. But I'm not sure they will disappear. It may be a bit too much, or I think if they disappear, there is a trick in the hardware to emulate automatically without precision lost. I think it's more this kind of stuff. If in fact if I have my input in float64, I do some magic in brain float or in integer or whatever, and I get my output in float64 and everything is okay. Okay, why not? If they disappear, you have more room to put more computing unit for lower precision, so it's better. So yeah, but I'm not sure they will disappear right now. Even for Rubin, they did not disappear. For FeynMind, I don't know, but we will see in few years. But for me, if they disappear, it's you have a clear path to emulate them. And maybe it will come at some point. Maybe you will have an emulation which is 100% proof, and you can emulate whatever you want, and it's okay. Maybe, or maybe the hardware will be able to do that. But yeah, there was a presentation about Ozaki scheme at GTC. Yeah, so I watched it yesterday, so I still have the link if you want to have a look. It's really interesting. It's quite technical, but you can get the most of the idea behind the Ozaki 1 and Ozaki 2 scheme, and some performances. Not all the feedback that you can get for other presentation, but typically if you want to have the feedback of weather forecasting or stuff like this, it's not in this presentation, but you can have quite a nice presentation also if you are curious. And you get all the replays. Yeah, of course, you get all the replays on YouTube. So everything is edited. So I do the editing, and normally everything is online on Friday. So you should have the replay, the slides, everything, all the link that you want. So if there is no more question, maybe we can stop here. Thank you, Marie. Okay, so let's wrap it up. So thank you everyone for joining us today. Hope it was interesting for you. Next time we will do some magic, as I mentioned, with Vincent. So Vincent will explain to you how to do this GPU computation with Fortran. So NVC plus NV Fortran, as for XVC++, you can emulate. You can use directly the GPU. You can also have some CUDA Fortran, and it has time to do some magic with CUDA Fortran. So we will notice also how to use them nicely. So thank you everyone. And okay, there is a lot of thanks in the chat, so it's the time to stop. So thank you everyone, and see you next week for some Fortran GPU stuff, and have a great week. Bye.